Hi, good afternoon. So today, if there aren't any more questions about the proofs in L of the GCH or AC or the axiom of constructibility, B equals L, I'd like to go back and look a little bit more at just ideas of consistency altogether. So section 3.5. We looked briefly at the correctness theorem from this, but I'd like to go back and do some other things from this section. So this is page 48 here. So this was correctness and consistency. Okay, just trying to. There we go. So, okay, probably does no harm to remind us about the correctness theorem. So the idea of the correctness theorem is that it links the two modes we have of talking about a formula being true in a structure. I might have a formula, so phi, say, and I could think of putting in some objects for some free variables here. So I've got a formula phi, and let's say it's got free variables. I think in the notes it's vj1 up to jm. So these are its free variables. Here's an m-tuple of objects here. So I can interpret this as saying, okay, I can relativize the formula to a structure, an x epsilon, just by restricting the quantifiers to x here. And we had this notion then of being true in the structure here. But we also have the notion of a satisfaction relation, where we coded up the formula by a set, and we defined mathematically a relation which said that if I sign free variables using y vector for those v's here, that the two things come out the same. Right? So it's just checking here that this works. So, and this is no matter what the formula is, or x, or what the y vector is. So this is saying for all x and for all y, which is an m-tuple from x here. We can prove in ZF. Indeed, we don't need all of ZF, ZF minus or less would do really here. And we can relate these two notions of truth together, truth via relativization and truth via satisfaction here. Again, as I said at the time, this would be a proof by induction on the structure of phi, right? And we're not going to do it. So now I'd like to venture further down the page today. Right? So we've got these sets of axioms, ZF and ZFC, and we've listed those in chapter 1. Right? But we list these again from the outside. We say we're going to study this V epsilon, and this is the language we're going to use to talk about it. But we've already seen that for a formula in this language, right, with epsilon equals, we've seen that we can define a code for phi here, which is a hereditary finite set. Yeah. So this is the Gödel code of phi. And again, I used this already up here. So definition 322 just says, it's just notation. I put corners around ZF to mean the set of codes or formulae. So this was the function that returned a 1 if U was a code of a formula. And again, notation we haven't used yet. AXU, sorry, AX0 of U or AX1 of U or AX9 of U. And basically, we're just going to say U is a code of, in this case, the axiom of extensionality. Where AXI of U is a code of an instance of the axiom AXI. I mean, for example, right, AX0 would be the axiom of extensionality.
Oh no, I was just wrong. Cool.
Okay. So the axiom of extensionality is there's one axiom of extensionality, right? So when we write it out in our official language, where we're only allowed to use not and or and exists here, as sigma say, then AX0 of U holds if and only if U is the code of sigma. But that was because the axiom of extensionality, there's just one unique axiom, it's just one axiom. But other axioms like replacement and separation, there are infinitely many possible codes U to put in here. So in particular, so for each I less than or equal to 9, AXI of U is the collection of codes of axioms of the form AXI, whatever that is. So ZF corners here, Gödel code of ZF, is just all of these formulae which are axioms, or codes thereof. And oh, I see, ZF, this should be 8, and ZFC adds axiom 9, axiom of choice. So they're just code sets, right? Again, being a code set is something that is definite. We can look at the shape of these axioms here and just determine in a definite way whether U is a code of the axiom of extensionality. There's only one specific thing it can be. But even for those which represent infinite collections of axioms, we can determine whether a code set is coding something of the right syntactic structure because after all, that's what the code contains, the syntactic structure. So we just have a lemma then. (323), which just says U is in ZF, corner ZF, or the same for ZFC, is definite. These are definite. And 2, if I is an axiom from our list, then actually in ZF or ZF minus, we can prove that the code of phi is in the code set. So again, this would be a proof by induction. There's infinitely many proofs, one for each phi, and we do it as a kind of meta-induction on the complexity of the structure of phi. So again, we say it's a theorem scheme, one theorem for each phi. Again, because these here are definite collections. Again, a bit more notation. All right, X epsilon, okay, validates all the axioms in ZF, the ZF code set. If and only if, and well, you can see it coming. Right? If for any code in the set X epsilon, U is satisfied in X epsilon. The axioms of ZFC are sentences, right? So we don't have to assign objects to the free variables of the axioms. Right? We consider them as sentences. So again, we have that this relationship, right, or this property of X is again definite. So it's absolutely definite between transitive models of ZF minus. Right? Okay, so that's the kind of setup. So we have a corollary to the correctness theorem, 325. So again, it's a scheme. For any phi an axiom of ZF, I seem to have written ZF minus. So I think this could be all ZF or ZFC. And ZF minus, we can prove. I put in a for all X here. seem to have just missed it out on the text. So insert for all x in the text at this point. If a structure is a model of this code set, because phi is an axiom of ZF minus, I suppose I could put in minus here. Then phi holds relativized to x epsilon. So this is just one aspect of the correctness theorem where we've just incorporated this notation for these code sets of formulae here. And the alternative versions would hold just as well, replacing ZF minus by ZF or ZFC. So it's just bringing out one direction of the correctness theorem there. Okay, that's perhaps all I want to say just at the moment on that. Let's go to 351, incompleteness and consistency arguments. So we've already seen some consistency arguments about L. We saw things like con ZF implies the consistency of ZF plus the axiom of choice. And various other things here, either V equals L or GCH. Right? So in general, for T a theory, so often a theory is just a set of sentences. So, or a set of things that we could think of that we're wanting to be axioms. So ZF is a theory as well. So we write con T. If for no sigma, do we have that T proves sigma and also T proves not sigma? And by rules of logic, that's the same as saying T proves sigma and not sigma. You can combine these two proofs to give a proof of the conjunction. So it doesn't matter how you want it. Right? If the language in which the theory states can express arithmetic, so if the language of T can express arithmetic, right? So maybe it's got symbols for 0 and plus and times and so on in it. Then you can write down your other favorite contradiction. So write down your favorite contradiction. Perhaps T proves naught equals 1. Or some such down here. Or 2 plus 2 equals 5. And that would also encapsulate the notion of T being inconsistent. So Gödel's argument about the incompleteness of theories in which you can express arithmetic involved the idea of finding that you could define within arithmetic the relationship between a code set of a theory and a contradiction, or the relationship between a theory and a collection of other numbers that coded lines of proof from those axioms. And perhaps the proof ended in 0 = 1. So what Gödel did he formulated a concept of formal proof well, I mean, he didn't do that. That's just something logicians have done for a long while, right? So, I mean, a formal proof, it's just a finite sequence of formulae. And some of these will be axioms, and some of these will follow from earlier ones by the rules of proof, modus ponens or generalization, whichever logic one is using. And what's being proved is the sentence down at the bottom here. And the point is that this is a completely algorithmic or mechanical process. If you know, you can decide whether something is an axiom in an algorithmic or mechanical way. So then you can just look at this thing that somebody's given you and says that it's a proof, and you can check it. So you just check that every line is either an axiom, and you can check whether something is an axiom or not, or it comes from earlier lines by one of your 2 rules of proof. It's a finite object, so each of these can be coded by sets or natural numbers. This is what Gödel used. And the whole sequence can be coded as a natural number. So then it's just a machine can just simply check, right, if it's given a code for a sequence of lines, whether that is a proof. It's an entirely mechanical method. So he formulated the concept of formal proof. And showed that something like V0, the variable V0, this relationship, V0 codes a proof in T of V1. This could be given an arithmetic expression, so it could be represented in a theory T. In a theory T, if T could represent enough arithmetic to do all of this coding. So the kind of standard theory of number theory, which logicians and again number theorists use, is called Peano arithmetic. So if T could also represent sufficient arithmetic to do this coding. So Peano arithmetic is, again, it's one of those things in mathematics that is a misnomer. It wasn't due to Peano at all, it was due to Dedekind. But it's grown up, this is called Peano arithmetic or PA. Is the accepted system of arithmetic. So as long as the theory T extends the axioms of Peano arithmetic, then it can do it. NZF is a very strong theory. It can prove anything about arithmetic that you want. So it's, sorry, that's a misstatement. It's it certainly can prove all the axioms of Peano arithmetic, because set theory can prove an awful lot more than arithmetical facts. So the point is that this here, this relation, V0 codes a proof in T of V1, right, can express that as a formula of T in the language of T. So V0 codes a proof of V1 in T. So PF for proof and a little superscript T is just this relation here, two numbers. But now one can express in T, or Peano arithmetic, what it means to be consistent. So we then can say that T is consistent. By saying there is no natural number which is a proof of naught equals 1. Right? This is about numbers. This is a code number of this formula. This whole thing here is about numbers. So I've expressed the statement T is consistent in this way here. So this formal consistency statement so this will be written with a, say, with a superscript T. So this is different from the con round brackets T we were talking about before. That was kind of much more informal. We talked about what we could deduce from the in logic from T. Right? This is a precise mathematical statement, right, about numbers here. So Gödel showed okay, that from T you can't prove con T. So this is interpreted that arithmetic cannot prove its own consistency in this way. This formula is unprovable, right, in the theory T, if T extends the axioms of PA. So what we have are the notions of like proof and contradiction, axioms, and so on, are all stated within the theory T. Now we started a little bit down that route where we talked about in ZF, we can define syntax. Right? We can say what it means for something to be a formula, a properly formed formula. We could go on and do the kind of Gödelian extension of that and talk about proofs in ZF in the same way. Right? In some sense, it'd be a little bit superfluous because ZF is so much stronger a theory than Peano arithmetic. And anyway, it's not part of this course to give a presentation of the Gödel incompleteness theorem. But actually, we can do a weak version of the incompleteness theorem, which is quite sufficient for any of our purposes. We give a weak version because it uses additional hypotheses. I should say that this is called the second incompleteness theorem. The first incompleteness theorem says there's a formula chi such that T neither proves chi nor not chi. So this was, I mean, for David Hilbert and his program for trying to put mathematics on a secure kind of logical foundation. This was a disaster. Right? He'd hoped that one could find some axiomatic system such that any mathematical statement could either be proven or disproven in that system. And what Gödel upended this by showing this is simply not possible. There will always be, doesn't matter what the T is, as long as it extends Peano arithmetic, there will always be some formula such that T neither proves it nor its negation. So that Hilbert plan was a dream. And then he went on to show the second incompleteness theorem here, that in fact, the system can't prove its own consistency. Yeah. So what we're going to do for today is version 326. Here. So Gödel. If informally ZF is consistent, then ZF does not prove that there is a transitive set model of ZF. So I've said before the consistency, well, the incompleteness theorem say that from a theory you can't prove the theory is consistent. Well, this is one way of saying it. You can't prove that there is a model of the theory, because if there was a model of the theory, of course it's consistent. Right? It means that all of the axioms here are true in this structure. So it's like saying the axioms of group theory are consistent because there is a group in which they're all true. So this is saying, right, we can't prove in ZF, well, it doesn't quite say that there are no models of ZF, although we could do this, but it will be more elaborate. What it says is there are no transitive models of ZF. This is kind of a weaker statement. We could say stronger things, but we don't, because this is easy enough and good enough for our purposes. Okay, now's the time to ask if any questions about the formalism or the setup before we proceed with the proof. Yeah, if you've got any. Okay, proof. Okay, let sigma be this sentence here. And we'll suppose that ZF can prove sigma. And we'll show that it's inconsistent. So this is very similar to the proof, well, there are aspects of this that are very similar to the proof that ZF is not finitely axiomatizable. Okay, so suppose ZF can prove sigma. So ZF can prove that there is a transitive model like this. So what we'll do is we'll think about the transitive model that we can prove to exist, and we'll consider one which has got least rank. So a set is somewhere there in the V hierarchy, it's got a rank. So we'll look for transitive models of ZF which have got least rank. We'll get from that a contradiction. So ZF proves sigma so ZF proves there is some Z which is transitive and Z epsilon is a model of ZF here. But moreover, for any other W, if W is transitive and the rank of W is less than the rank of Z, then W is not a model of ZF. So the Z here that instantiates this is going to be something of least rank. So it's the least complicated in terms of the V hierarchy set, which is a model of ZF. So I've called this star in the notes, this statement. Okay, so let Z satisfy this formula. Right. Okay, by the last, well, so by the corollary above, this means that for any axiom phi from ZF, it's true relativized to Z. Another way I could say this is for phi in ZF. So we have that phi holds in this structure Z epsilon. So in other words, all of ZF holds if you relativize the quantifiers, restrict them rather to Z there. So I've got a Z here in which all the axioms of ZF are true. On the other hand, it's supposed to be the case that I can prove sigma from ZF. So if all of these axioms are true in Z, so is sigma by soundness. Hence, sorry. And perhaps you can see it coming now, right? Sigma asserts the existence of a transitive model of ZF. Okay. Sorry, my connection seemed to cut out for a moment there. Okay, this is where we were. Sigma holds in Z, but sigma asserts the existence of a transitive model of ZF. And there can't be any such elements in Z because Z was chosen specifically so that there were no such W's of smaller rank than that of Z. And any W in Z that was a model of ZF would have to have smaller rank. And this is what the contradiction will be. So I write this out, perhaps somewhat unnecessarily in full. So I write out sigma again. All of this here holds relativized to Z. So pick a Y that makes this true. So on the closing straights, we'll get the contradiction. So let Y be in Z so that it's transitive and Y epsilon is a model of ZF in Z. And now by the work that we've done, these concepts are definite. Right? Being transitive, this is a definite collection of codes. This is a definite relationship between this set and this structure here. So this holds if and only if it holds there in V. So, but this is here a definite formula. This is a transitive ZF minus model. So I have this. Here. And now, as I've said, as because Y is in Z, its rank is less than Z. Y in Z implies the rank of Y is less than the rank of Z. So this contradicts star up here. The point was the Z we chose, there was nothing of smaller rank, which was a ZF minus model. So this contradicts the choice of Z at star. So this shows then that ZF is then inconsistent here. We've got a contradiction. So we thus have a contradiction. And so ZF is inconsistent. Over here. Okay, any questions then? I mean, you might have a kind of uneasy feeling about this. And it might go the following way, right? Here. From your logic course, you may remember that there was Gödel's completeness theorem. And the completeness theorem said, if you've got a consistent set of sentences, then there is a model. So if ZF is consistent, right, we look at the formalized version of that, right, within ZF set theory. And, I keep claiming that we can do all of mathematics in Z theory. So why can't I prove the completeness theorem then as part of set theory, and then I prove the completeness theorem. The completeness theorem then says any consistent set of sentences has a model. So if ZF was consistent, I could prove the existence of a model of the axioms of ZF. Right? So I might think, okay, so you don't have to remember this or pay any attention to this. We can prove the completeness theorem. Right, in ZF. It's just a theorem of mathematical logic. And so like any other mathematical theorem, could be proven in ZF. So what we would have then is something like this. We'd have a proof in ZF that if ZF was a consistent theory in the way I was outlining above, then the Gödel incompleteness applied to this consistent theory would say, okay, there is an X and there is an E. And indeed, in the Gödel completeness theorem, it says you can actually take the model to be countable. Okay, so it's got size omega and XE here is a model of these axioms ZF. But isn't this just contradicting what we just did? Right? Well, the answer is no. Right? What we just did was talk about transitive models. So we talked about transitive models. X epsilon. Right? And that's not what the completeness theorem provides. The completeness theorem provides a completely artificial model. It builds a model out of equivalence classes of the syntax of the language. So not necessarily anything to do with sets at all. And the E relation that it'll define, again, was not necessarily anything to do with epsilon. It's just a binary relation, such that I interpret the sentences of ZF in this structure with epsilon interpreted as this binary relation. They happen to come out true, which was why we were building the model in the first place by the completeness theorem. The completeness theorem only delivers models X made of equivalence classes of formulae. Well, depending on which version of the completeness theorem you look at. If we look at the Henkin version of the completeness theorem, and a relation E on them. But E has got nothing to do with epsilon. And indeed, We talked about transitive models. Well, set membership is well-founded. There is no reason to think that this is a well-founded relation either. There's nothing in the completeness theorem proof that delivers a well-founded E. And indeed, you can show, as some of the exercises there give us, the structure provided by the Gödel completeness theorem. I mean, in many cases, this is of necessity ill-founded. Right? So this E will have descending kind of chains of equivalence classes going through it here. So in general, this will be ill-founded. So it doesn't contradict the theorem 326. Okay. Okay, so that's just a note about the relationship of that theorem to the completeness theorem, in case you were thinking, or somebody was thinking, that this would be giving us a contradiction, or that we were wrong in saying that.